Welcome back to day 3 of bending stress. To start things off today, I wanted to finish an example that I started in the very last video involving this simply supported beam is symmetrically loaded with a pair of 25 kip loads. We discovered last time that the reaction forces will then both be 25 kips pointing upward, and that gives us a shear force diagram that looks like this. The things to notice on this shear diagram is all of our slopes are 0 because we don't have any distributed loading, and we just have jumps up and down 25 kips and down and up 25 kips. From that, we then got our moment diagram to look something like this. It's going to have a positive slope of 25 at the beginning. It's going to end with a negative slope of 25. It starts and ends at 0 because we don't have any applied couple moments. And in the middle, where our shear force is 0, our bending moment has a slope of 0. So our max bending moment in this beam is going to happen all along that middle section. This is something called 4-point bending. It's used to test materials in bending because you get this nice long section in the middle of the beam with a constant bending moment. Let's review how we figure out how big that max bending moment is. We're going to find it by calculating area 1. It's a rectangle, so we'll just take one of the sides, 25 kips, times the other side. This length is 20 inches in this problem. And when you multiply those together, you get 500 kip inches. And remember, the area under your shear diagram tells you, in going from point 1 to 2, what is this change in M. So that's going to give us our M max of 500 kip inches. So let's finish the problem. Now we know the max bending moment. We can find the stress. We have kind of a complicated cross-section. It is an I-beam, but it is not symmetric. So before we can do anything, we're going to have to find where is the centroid of that I-beam. So I've drawn it out a little bigger down here. Finding a centroid, you always want to define a reference axis. I chose to use the axis at the top. Let's first color code our shapes. So if we have one shape is green, one rectangle could be blue, and let's make the last one pink. I'm going to need to find the centroids of each of those shapes and plug them into my formula. Formula for the y location of a centroid is you add up all of the y tildes. Those are the centroids of each shape, multiply them by their area, and then divide by the total area. So we'll need a great big long fraction. Let's start with that green rectangle. The area of the green rectangle is going to be 8 inches times 1 inch. That goes in both the top and the bottom of the fraction. Then I also need to know where is the centroid of that rectangle. That's right at the middle of the rectangle, half an inch down, and since that rectangle is located right on my reference line, the location is just 1/2 inch. Let's do the blue area. It's a 6 by 1 rectangle, so its area will be 6 by 1. That goes in both the top and the bottom of the fraction. And its centroid location, it will be at the middle of the rectangle. Since the rectangle is 6 inches tall, it'll be 3 inches from either side of the rectangle, but that is not my reference line. My reference line is another inch farther away. So 3 plus 1 is 4 inches. Finally, adding my pink rectangle, it is a 4 by 1. So we'll have 4 inches times 1 inch in both the bottom and the top of the fraction. And its centroid will be at the middle of the rectangle. It's a 1 inch tall rectangle, so that centroid would be 1/2 inch from the top or bottom of that rectangle. But to get all the way to the reference line, I've got to go 1/2 inch plus 6 plus 1, which should be 7.5 inches. We multiply that all out and we get 3.22 inches, and that is measured from the top. Some students would prefer to put their reference axis at the bottom and get a number from the bottom. That's perfectly fine as well. And in fact, I want to get that number as well. So the overall centroid came out to be right about here, 3.22 inches. The distance from the centroid to the bottom would be the whole height, 8 inches minus 3.22. That comes out to be 4.78 inches from the bottom. And the reason I'm calculating that is I'm going to need it later. We want to find the stress in this at the top and the stress at the bottom. So I need the distance from the centroid to the top and the centroid to the bottom. Now that we have our centroidal location, we can find the moment of inertia about the axis through that centroid. We need to add it up for our 3 areas. Let's start with our green rectangle, 1/12. The base is 8 inches, the height is 1 inch, and that gets cubed. Now that'll give you the moment of inertia of the green rectangle about this axis, but that's not the axis we needed about. We needed about the axis through the black dot that I just drew. So I need to add to it, we're using the parallel axis theorem here, I need to add to it the area of the green rectangle and this distance squared. So let's add to it the area, 8 inches times 1 inch, and that distance would be, the easy way to find this distance is grab the y bar value you just found and subtract from it the y tilde value used in your equation. 3.22 inches minus 0.5 inches, and then that number has to get squared so that the units work out. And what I'm doing is this is the distance from the reference line to the centroid of the whole shape. This is the distance from the reference line to the centroid of the green shape. So if we subtract them, we will get this nice little distance between the two centroids, which is what we need. Let's move on to the blue rectangle. Same exact process. 1/12, its base is 1 inch, its height is 6 inches, which gets cubed. You're always cubing this vertical distance because we're finding moment of inertia about a horizontal axis. We add to it the area, 1 times 6 or 6 times 1, and then the distance between the two centroids. So the centroid of the blue rectangle was 4 inches from the top. So 4 inches minus 3.22 inches will give us the distance between the blue and the black dot. We square it. And finally, let's do that pink rectangle. 1/12, its base is 4 inches, its height is 1 inch, which gets cubed. Add to it area, 4 times 1, and the distance between the two centroids. So that pink rectangle had a centroid all the way down at 7.5 inches. Subtract from it 3.22 inches and square it. The number comes out to be 155 inches to the fourth. So now we can find stress. So if we want to find the stress at the top, our equation is my over I with a plus or minus. We found the moment earlier. The max moment was 500 kip inches. And the y location for the top, what we're doing is, remember, we always in this equation are measuring how far are we from the centroid. The stress is 0 at the centroid, so if we want the stress at the top, I need 3.22 inches. And my moment of inertia is 155 inches to the fourth. And now we need to figure out if that top is going to be in tension or compression. The way we do that is we actually look at the sign of the bending moment. Bending moment positive, if you remember your sign convention, if I cut open a beam and look at the internal bending moment, this is what we defined as positive bending moment. So you remember with a positive bending moment, those arrowheads are pushing in on the top of the beam. So we get compression on the top and tension on the bottom. So when I found the stress at the top, I need to put a negative sign in front of it and call it a negative. It comes out to be 10.4, and the units are kips per square inch, or KSI, and the negative means compression. If I want to find the stress at the bottom, exact same equation. Stress is plus or minus my over I. The moment is the same, 500 kip inches. The moment of inertia is the same, 155 inches to the fourth, but the distance is different. I want to go to the bottom, so I want to use 4.78 inches. And doing all that math, the number comes out to be 15.4 KSI, and that is tension. Because if it was compression on the top, it has to be tension on the bottom. So if you want to put a plus sign in here, that would be great. That's it for our simple example that we started last time. I want to spend the rest of this video doing a fun example. I usually teach this class fall semester in the heart of football season. So the example I want to use is actually football uprights. You guys have seen them if you've ever watched a college football game, and I did take this from the college football uprights, which are different than the pro football uprights. So looking at it from, where the kicker would be looking, you've got what are called uprights on the side. They are made up of 60-60-61 T6 aluminum, 4-inch outer diameter with an 1/8 inch wall thickness. So that is what those cross sections look like. And using this, I looked up the density of aluminum. I calculated based on the fact that the uprights are 20 feet tall. With this area, I found their volume, and I found that the weight of each upright is 35.8 pounds. They are connected to this crossbar. This is what the football has to go over in order to score an extra point or a field goal. Crossbar also made of 60-61 T6 aluminum, but it's got a bigger diameter and a bigger wall thickness, and the reason is it's got to handle a whole lot more load. We're going to actually analyze a crossbar in a minute. I want to look at the loads on a crossbar when it's just sitting there with just its weight on it, as well as when some celebratory students might have climbed on said upright to try to pull it down at the end of a big victory. So there's our crossbar information. Now, these are supported by this support bar, and I'm just showing a front view of it. If you turn it on its side, it's actually got curvature to it. We're not going to analyze that part because to analyze it requires a lot of mechanics that we don't get into in this class, a little bit too advanced. I'll talk about a little bit at the end. So we're going to analyze the crossbar and look at how close is it to failure. But if you ever wanted to, this guy is actually made of steel, galvanized steel, similar outer diameter, but a thinner wall thickness. Let's begin our analysis. And I want to start with just the weight of the materials themselves. It's basically a beam with a hollow circular cross section. It's got uprights on each side pushing down on it with 35.8 pounds. We're going to include the weight of the crossbar. I took the density of 6061 T6 aluminum. I took the cross-sectional area and the length. This is roughly 19 feet long. I figured out the total load and I divided it by the length to get a distributed loading here of 4.91 pounds per foot. That is the weight of the crossbar itself. Those are all downward loads. What's holding it up? What's holding it up is this steel post. And we're not going to get into the details of how they're connected and what that looks like. The end result is, since this is perfectly symmetric loading, it simply needs to apply an upward support force. For the 2D analysis of this crossbar, that's going to be sufficient. Weaken some forces in the y direction to solve for that support force. If we do that, we've got the support force upward minus 2 of those 35.8 pound loads from the uprights minus 4.91 pounds per foot times the length of that crossbar, which I converted into feet is 19.17 feet long. That all has to equal 0. And doing that, we can calculate the force in the support, which comes out to be 166 pounds if we round it. We need to figure out how big the stress is. So to do that, we will need shear force and bending moment diagrams. Let's start with the shear force diagram. The first thing that happens on this beam is we go down 35.8 pounds. So we're going to start out down here at minus 35.8 pounds. Then we have a downward slope for a while. Then we're going to reach that support force. It's going to cause us to jump up a bunch. And since that loading is symmetric, I'm going to use the fact that I expect this to be an anti-symmetric drawing when I'm done. And let's just sketch it out. And we'll put some numbers on it. We're going to keep going down at that same slope. And then at the end of the beam, we've got another 35.8, and we should end up at 0 when we're done. So I think it's going to look like that qualitatively. Let's put some numbers. We were down 35.8, and we go down at this slope of 4.91, where are we going to end up? Well, that would be the area under the first half of this loading curve. So call that area 1, and let's go calculate it. The height of that is 4.91 pounds per foot, and it acts over 19.17 feet over 2, half of the beam. So you multiply those out and you get 47 pounds. So going from our 35.8 pounds, we're going to go down 47 pounds. So you subtract 47, then we're going to end up down here at minus 82.8 pounds. Then we jump up 166, which I should have kept more decimal places. We're actually going to jump up 165.7 pounds, which is basically going to take us to positive 82.8 pounds. Then we're going to go down to that exact same 4.91 slope for the same amount of distance. So that means we're going to come down to plus 35.8 pounds and then back down to 0 at the end. From that, we then are going to draw the bending moment diagram. What's the bending moment diagram going to look like? We expect it to be symmetric because our beam is symmetric. We are going to start with a negative slope, and that negative slope is just going to get more and more negative, starting with a negative slope, but ending up with a much more negative slope with a parabola. Then all of a sudden our slope switches signs. So we're going to have a cusp and we're going to go back up kind of like that. And what matters for this diagram is M max. We need to figure out how big it is. So the way we do that is we need the area under this part of the curve. I want to break that up into a rectangle and a triangle. Let's do a blue rectangle and a green triangle. So if I can find those two areas and add them up, I will be able to find out how big is M max. Area 2 first, that's going to be 35.8 pounds is one side of it, and then the other side is half of the length of the beam. So 19.17 feet divided by 2. Again, that number comes out to be 343 pound-feet. And then let's do our green area 3. That's a triangle, so 1/2. One of the sides is this 47 pounds. That's the difference between these two. So plug in our 47 pounds, and that also acts over half of the length of the beam. Area 3 comes out to be 225 pound-feet. You add those up and you get M max equals 343 plus 225, which is 568 pound-feet. Now we can use our bending stress equation. Our max stress is going to be my over I. Well, what was our cross section? Cross section was a circle with a hole in the middle of it. Moment of inertia of a circle in general is pi over 4 radius to the fourth. So the moment of inertia for this circle, outer circle minus inner circle, so pi over 4. What is the radius of the outer circle? This is the crossbar. It has a 5 9/16 inch diameter, so you got to divide that in half. So that outer radius is 2.78125 inches, which gets raised to the fourth, and I subtract from it pi over 4 times the inner radius. Well, what was that? Oh, it had a 1/4 inch thick wall. So that means I can just take my outer radius and subtract 0.25 from it. So I get 2.53125 inches, which also gets raised to the fourth. And that number comes out to be 14.7 something inches to the fourth. Now we can find stress. Max stress, it'll happen right here in the middle of the crossbar. It's going to be our moment, 568 pound-feet. And I don't want to leave feet in there. Let's convert that to inches right away. I've got 12 inches in 1 foot. The y distance, oh, well, the y distance is what is the farthest you can get from that centroidal axis? That'll be that outer radius, 2.78 inches. And then in the denominator, we put our 14.7 inches to the fourth. And the number that comes out is 1290 psi for 6061 T6 aluminum. The yield stress I look up is 37 ksi. Let's do a factor of safety. Factor of safety is always the stress that will cause failure divided by the actual stress. 37, let's make it psi, 1000 psi, divided by 1290 psi. This is not going to fail, guys. 28.7 factor of safety. It's way, way bigger than 1, so this is very, very safe and will not fail under its own weight, and that shouldn't surprise you because we don't have these things just breaking off randomly while they're sitting there. So let's add some students. Let's make this interesting. I'm sure you've probably seen footage of a football game where some students stormed the field and they got on top of the crossbars and they brought them down. So let's see how many it would take. Adding some students. Here's our crossbar. We still have the weight. So we still have 35.8 pounds on each side from the uprights. We still have the overall weight of the crossbar itself, 4.91 pounds per foot. Now we got to add these students. Let's say each student weighs, on average, 170 pounds. And let's say there are 10 students. Well, we could manually draw a whole bunch of 170-pound forces and mess around with where they were. But I think it's not a bad approximation to just say, those 10 students will create another distributed load. 170 pounds times 10 students divided by the length of the beam. And at this point, I decided to be a little bit approximate or make this all go more quickly. And instead of dividing it by the whole length of the beam, I just said the beam is roughly 19 feet and I left off the 2 inches. Hopefully you don't mind that approximation too much. So you end up getting 89.5 pounds per feet is what we're going to apply to this. That's approximating 10 students on the beam, assuming that on average they weigh 170 pounds. So it's a total of 1,700 pounds of students spread out evenly over the beam. Let's look at what that does to our shear force and bending moment diagram. Oh, let's not forget, we also still have a big support force here, which is going to be bigger because now we've added some students. So let's draw our shear diagram. Qualitatively, it's actually going to look very, very similar. We start down at minus 35.8 again. And we're going to go down, but this time we're going to have a much steeper slope because instead of just going down at a slope of 4.91, we're going down at a slope of 4.91 plus 89.5. So this time our slope is 94.4. So we're going to have a whole lot farther down. And then we're going to jump up with this much bigger support force. And then we go down again, same slope. And we should end up again at plus 35.8. To figure out how far down we're going to end, let's actually do the math. We've got this piece and we've got this piece. We're going to add them both. So if we do area 1 was still 47 pounds, but now area 2 is 89.5 pounds per foot times half the length of the beam, but we're just going to call the beam approximately 19 feet, so that'd be 9.5 feet. That one comes out to be 850.25 pounds. So add those two up. We've got to add 897 pounds to our 35.8, which takes us down to 933 pounds. We do our support force, that's going to kick us up to plus 933 pounds. And then we go down again. Our shear force diagram looks like that. Just like last time, from there, I would want to take this rectangular area and this triangular area, and that's going to give me M max. Call that one area 3. That's again 35.8 times half of the length of the beam. It'll be exactly what it was before, 343 pound-feet. The green one, area 4, that one's going to be 1/2. 933 minus 35.8 is 897 pounds, and it acts over, we're calling it 9.5 feet. We get 4261 pound-feet. Same exact picture as before. It's going to start negative and then switch and going up. What matters is this M max. M max would be the sum of your area 3 and your area 4 up there. Comes out to be 4,600 pound-feet. Let's use that information. Same equation as before. Sigma max is always my over I. We are now going to plug in 4,600 pound-feet, convert from feet to inches, so 12 inches in 1 foot. We're going to plug in our y value, which is the same radius we used before, 2.78 inches, and we're going to divide by the moment of inertia, which was 14.7 inches to the 4th. We do that math, and we get 10,400 psi, or 10.4 ksi. So let's do our factor of safety again. The yield stress is still 37 ksi. Our actual stress with these 10 uniform, perfectly distributed students, 10.4 ksi. So we still have a decently comfortable safety factor of 3.6. So I do not expect the crossbar to fail from these 10 students. Without going through all of the detail, I thought, well, what if we ramp up the number of students? If we bump it up to 20 students, what happens is the max stress goes up, not exactly double, but close to it. Now it's 19.1 ksi, and our factor of safety looks like 37 divided by 19.1, which is 1.93. What if we doubled it again? 40 students. Well, then our max stress, again, it doesn't quite double because stationary weight of the uprights doesn't change, but we did double most of the loading. So it jumps up to actually to 37.3 ksi. Now look what happened to our safe factor. 37 ksi is the most you can ever have, but we actually have 37.3 ksi. We get a factor of safety less than 1, just barely. And so this would fail. So you can't put 40 students evenly distributed on there without the crossbar failing. But if you look at video footage of these failing, they usually fail a whole lot sooner than 40 students. I don't have an exact count, plus students don't all weigh 170 pounds. They fail a little sooner than that, and there's a few reasons why. So first of all, let's go back and say, what if they're not uniformly distributed? If you look at how students climb on these things, and I am not encouraging anyone to ever do that, but if students did climb on it, you typically notice a bunch of extra students on each of the uprights because they've got something that they can hold on to. And then they're less concentrated in the middle. So why don't we go back to our 20 student case? And instead of having those 20 students uniformly distributed, let's put 5 on each upright and then have 10 of them spread out. One more case to look at. So let's try 20 students unevenly distributed. We do still have our 35.8 pounds from each upright. We'll still have our support force in the middle. We got the weight of the actual crossbar. That's the 4.91 pounds per foot. We have also the weight of the 10 evenly distributed students, which was 89.5 pounds per foot. So we're basically doing our 10 student analysis again, but then what I want to add to it is a giant 5 students on each end. So that would be 850 pounds if they average out to 170 pounds per student. 850 pounds equals 5 students. And the 89.5 is equal to 10 more students. So it's 20 students, but they are grouped toward the ends. Let's look at our shear force diagram. The overall shape of it's going to be the same. We start off with, instead of just going down 35.8, we're going to go down 35.8 plus 850. So we're going to start out all the way down here at minus, turns out 886. Then we're going to go down at a slope to the middle of the beam. Then we're going to jump up just like we have all along. Then we're going to come down this way and then go back to 0. And we will again be at 886 is what that should have been. And these peak values are going to end up being 1780 at the bottom and 1780 at the top. I don't think I got quite high enough at the top. Anyway, pretend with me. 1780. This should be anti-symmetric. Then what's our moment diagram going to look like? You guys know what the moment diagram is going to look like. It's going to look just like all the others. It's going to be these concave down parabolas with a cusp in the middle, and we need to know M max. To do that, again, we just need to find the area of the rectangle plus the area of the triangle. That'll give us M max. So it's going to be 886 pounds times 9.5 feet plus 1/2 of the difference between 1780 and 886 is 897 pounds, also acts over approximately 9.5 feet. So my M max comes out to be 12,680 pound-feet. And when we plug that in to find our max stress, it's going to come out to be 28.7 KSI, giving us a factor of safety for this material of 1.29. Do you see the difference? When we had our 20 students evenly distributed, we were up at 1.93. Take that same amount of weight and distribute it differently, and now you're down to 1.29. Again, not likely to fail if the students stay still and don't move and are distributed just like this. This is as far as we're going to go with our numerical analysis, because this is about as far as you can go using what you guys know in mechanics at this point. But there are a couple of things that happen in real life that are the reason that I think 20 students can easily take one of these down. The first is, if you see the students on the uprights in videos, they oftentimes start rocking this back and forth. They'll get this side to rock down and then that side to rock down. Whenever you add dynamic effects, materials fail sooner than if the loads are purely static. All we can analyze in this class are static loads, but once you add dynamics, failure occurs sooner. Also, by rocking first one way and then the other and then back and forth, you're adding an element of fatigue. So you can't just use the plain old yield stress once you add fatigue to your loading. You have to do a more in-depth analysis, again, beyond the scope of this class. Finally, if you look structurally at where these uprights tend to fail, in every video that I've been able to see that level of detail, they typically don't fail in the crossbar. They typically fail in this support post. If you looked at this on the side, if here's your upright crossbar coming out of the page at us, that support bar has this curved shape to it. And in that curved shape, it usually fails somewhere around there. Well, we could analyze and figure out the static stress right there. I don't think that it's terribly relevant for updating our analysis right now, and here's why. So first of all, that area right there, if you get this rocking back and forth, it's going to be experiencing both bending and torsion at the same time, so a fairly complex stress state. Typically what happens is that the hollow cross sections actually start to crimp and crush. And that is related to a kind of buckling instability that, again, is beyond the scope of what we can do in our class, and also will tend to cause things to fail at a much lower load. 4 things tend to cause this to fail sooner than our analysis would predict. 1 is the dynamic loading effect. 2 is the fatigue loading. 3 is the combination of bending and torsion in that support post. And 4, finally, is the instability that happens with crimping of thin tubes. So we can't do any better than this with our mechanics analysis, but I hope this gave you an idea of how when you see something out there in the real world that has loads on it, you can actually use your tools to calculate bending stress. You just may need to do a little bit of research on what material is it, how long is it, what is the cross section. But once you can find moment of inertia, you can get some stress values to get a sense of how close is this to simply failing due to static loading. Then in later classes, you may get to learn about dynamic loading and crimping and crushing and fatigue loading. Thanks for watching. Hope you had fun learning a little more about bending stress and applying it to football goalposts. See you next time.